So I want to talk about some joint work with a PhD student of mine, Tristan Bookmaster, and Camillo De Lellis. And the basic topic that we are after is the limit case of the Navier-Stokes equations, the Euler equations, and in particular a phenomenon that is well known in turbulence, the phenomenon of anomalous dissipation. So anomalous dissipation is the following phenomenon. If you take the Navier-Stokes equations with the viscosity nu, then divergence of V also 0, then the energy dissipation rate epsilon is, at least formally, it's nu times the integral of the gradient of V squared. And now, after non-dimensionalizing, you have two quantities to consider. First of all, the Reynolds number, which is the typical velocity u times the typical size in the domain divided by nu, and the renormalized energy dissipation rate, which is epsilon. If you check what is the dimension of it, it's u to the power 3 divided by L, so you have to divide by it. And the phenomenon that is observed experimentally is, roughly speaking, saying that as the Reynolds number goes to infinity, then this quantity converges to some positive number, strictly positive number. Okay? So seemingly it contradicts with what might expect on first sight, that if nu is going to 0, then the energy dissipation rate should go to 0. But you have to be a bit careful with the renormalization. Okay, so this is, let's say, experiment and numerics. Since almost 100 years ago. Well, the experiment is 100 years ago, the numerics is more recent. Now, Kolmogorov founded the statistical theory of turbulence in 1941, and so it's a statistical theory in the sense that he assumes that there is a kind of ensemble of solutions of the Navier-Stokes equations, and in a suitable sense you can consider this limit. And he made several assumptions on this ensemble. One is the kind of homogeneity and scale invariance, or isotropy, and the other condition is the existence of this number, this positive number. And based on the existence, so assume there exists this number, which is positive, he came up with several scaling scales, several scaling statements. One of the most famous is concerning the energy spectrum. So the energy spectrum is the energy per unit frequency or wavelength, sitting at wavelength lambda, and so he derived the following estimate. So this scales like epsilon to the 2/3 times lambda to the minus 5/3. Now I don't want to define more precisely what is the energy spectrum, but the picture to have in mind is the following. So here is what people can also observe in experiments. If you take the logarithm of this E of lambda plotted against the logarithm of lambda, then there are three regimes. There is a kind of regime of low wavelength, which is not universal. It depends on the type of boundary and the experiment that you make. Then there is an intermediate regime, which is almost exactly linear, with this slope -5/3. And then there is a final very high wavelength regime where the energy is dissipated into heat by the viscosity. And what I want to say about this picture is that you can imagine this being the plot of the amplitude of the Fourier coefficients square. If you imagine, a solution of the Navier-Stokes equations written in Fourier series. So this decay gives you a certain, or you can interpret it as a certain regularity of your solution. Now, and so his prediction, this -5/3, agrees very well with the experiment. Although this simply comes from dimensional analysis, assuming that this epsilon and the lambda are the only parameters you can write. Okay, so almost at the same period, Onsager was also looking at this problem of anomalous dissipation, and but he had a different approach. So his approach was to say that if he assumed that there is this phenomenon, then, well, at least formally speaking, we could take nu to go to 0, or take it equal to 0, and then in principle there should be no dissipation. But so we are considering the Euler equations. And the question is it possible that the energy is not constant for the Euler equations? And so, of course, if you take a smooth solution, it cannot be true. For a smooth solution, the energy is constant. And so he discussed weak solutions. And in particular, he discussed weak solutions with a certain Hölder continuity. So something like this for some exponent alpha. And he made the following observation, which is now called a conjecture. Well, so first of all, if alpha, so if you have a weak solution of the Euler equations with this Hölder continuity, then if alpha is bigger than 1/3, the energy is constant. And this 1/3 is sharp. So if alpha is less than 1/3, then dissipation is possible. Of course, it's not saying that any solution with alpha less than 1/3 has to have dissipation, but it is at least possible. And he had already a very good calculation to imply part A of this conjecture. Now, the part A was then, the calculation of Onsager was made rigorous by Eying in 1994, where the paper appeared, and there is the modern proof is due to Konstantin E and Titi from 93. And I want to explain the basic idea of their proof. So first of all, so let me mention that, so I said here, if you interpret this decay of the energy spectrum as a statement about the decay of Fourier coefficients, then you get a certain regularity, certain partial, sorry, not partial, fractional differentiability of the solution, and it would correspond exactly to 1/3. So this 1/3 is in exact agreement with the 5/3 of Kolmogorov. Okay, it's the same. It's the same statement in terms of dimensional analysis. But I want to also emphasize that the Kolmogorov theory came from an assumption on certain statistical ensembles and the assumption that this epsilon is positive. Onsager's 1/3 is a, if you like, a PDE question. You take an equation, you take a weak solution. Does it satisfy an identity that is satisfied by smooth solutions? So it's already pretty remarkable that you get the same, you get agreement between these two numbers. Okay, so let me give a sketch of the proof of constantinicity. So basically, the idea is to just regularize the solution. So mollify V, so let's call it V epsilon. And then V epsilon satisfies this equation. There's also a P epsilon. And then there is a right-hand side that appears because the mollification does not commute with product. So there is V epsilon times V epsilon minus V times V epsilon. Okay, let me call this R epsilon. So you can, now everything is smooth, so you can now perform the usual calculation for the energy conservation, multiply this by V epsilon and integrate. And this term drops out again, and the pressure also, so you will end up with the following thing. So if I integrate in x and t, then I will get that V epsilon x capital T squared minus V epsilon x 0 dx. Okay, I was not at all precise about the domain, but I want to state that, so just for simplicity, x is in the three-dimensional torus. But this is really now not an important issue. It's just, you could do many of the things that I'm telling you also in R3, or even in domains with boundary. So you get the calculation that this is equal to the time integral of the space integral of, perform one more integration by parts, gradient of V epsilon times R epsilon dx dt. Okay, and then the question is, if epsilon goes to 0, does this quantity go to 0? And then just from the, so assuming that V satisfies this condition, the usual mollification estimate tells you that the supremum norm of the gradient of V epsilon, so this will be for me the supremum norm, and that's the only norm I'm using in this talk. This can be estimated by epsilon to the alpha minus 1 times the alpha Hölder norm. So it's the other norm I'm using. Sorry. And there is a slightly more tricky estimate for R epsilon. Well, you expect R epsilon to go to 0 because V epsilon is converging to V, and V times V epsilon is converging to V times V. But since this has a commutator structure, you will gain a power of epsilon, sorry, power of epsilon times alpha, so it's going to be 2 alpha, and then the Hölder norm squared. Okay? So this is a kind of commutator. And it's the same estimate that is used in the, for instance, theory of renormalized solutions of the Pernalions. Okay, so then you will see that the right-hand side can be estimated by epsilon to the 3 alpha minus 1 times the time integral of the Hölder norm at time t of V to the power 3. So if, okay, so A holds. Oh, so first of all, if the function is Hölder continuous with exponent alpha, alpha bigger than 1/3, then you see that this quantity is going to 0. And moreover, you see that even if it's not uniformly Hölder continuous, but this quantity is bounded, then it's still converging to 0. So if, let me say it like this, 1/3 plus. So any alpha bigger than 1/3 to the power 3, if this is finite. And then you can actually be, if you are slightly more careful with this commutator estimate and how you estimate the integral, instead of supremum norm, you can do something better and get a Bezov space statement. But this is sufficient for my talk now. Okay, now this is, roughly speaking, what is known concerning part A, and so part A is essentially solved. And concerning part B, that's the main topic of my talk. So I'm now in this talk going to just concentrate on weak solutions dissipating energy which are at least continuous. And just mention that there is a whole bunch of results about weak solutions which are discontinuous and dissipate energy, but that seems to be a slightly different direction, and I don't really have time to discuss that. And I'm hoping that Andrei will maybe say something in his talk later this morning. So concerning continuous solutions, and now, I mean, the definition of the solution, you can take still the distributional definition of a solution, but it's just as well to consider simply continuous functions. Okay. And then definition of a solution is just how you derive the Euler equations from continuum mechanics for any volume, any part of the fluid enclosed in some region with smooth boundary. You can perform the divergence theorem and get the continuity equation for that volume of fluid. Okay, and so there are two types of statements. The first type of statement is that given a function e of time, which is positive and smooth, there exists a weak solution, Vp, such that, well, first of all, there is this Hölder continuity. X minus y to the alpha. Okay, smooth and, yeah, most important thing, and given alpha, which is less than 1/5, there is this Vp with this Hölder continuity, and such that the energy, so V of xt squared dx, is equal to E of t for all time. That's the first type of result. So it's saying that at least with 1/5 instead of 1/3, in this class of weak solutions, you can prescribe the evolution of the kinetic energy in whatever you want. It has nothing to do with the evolution equation for momentum and mass. Okay, and so this statement is due to Bookmaster, De Lellis, and myself. 13. And there's another type of statement which is slightly better in terms of the regularity of the V, but slightly worse in terms of the statement. So there exists a weak solution, again continuous, with compact support in time, such that, and now, so it's a type of the statement. So there are 3 different statements, depending on, so 3 possibilities of what extra assumption the V fulfills. So the first statement is, well, so there was a statement like this for okay, so 1/5 Hölder continuous, as above. This is due to Iset, Phil Iset, in his PhD thesis, and it was in fact a predecessor of this result. The second type of statement, the second theorem is that for almost every time t, there exists a constant Ct such that the Hölder continuity holds with that constant, depending on time, but with exponent, well, 1/3 minus. So any alpha, you think again the same statement. So given alpha less than 1/3, you have the statement. And this is due to Bookmaster. Also 2013. And the third statement is very recent, is an improvement of the second statement, that the time integral of this 1/3 minus Hölder norm is finite. And this is, again, the 3 of us. The preprint just appeared a couple of weeks ago on arXiv. So if, I mean, this is currently the best regularity that we can achieve for a weak solution that does not conserve the energy. But I want to emphasize that here, the only thing we know is that the weak solution has compact support in time. We get some control of the energy, but we cannot prescribe the energy as in this theorem A. Okay, but on the other hand, you see that in terms of what is required for energy conservation, we are at least in the same range concerning the spatial regularity. We are lacking the integrability in time. Okay, so I want to use the rest of my time to give you a rough sketch of the technique. So all of these results are based on the same construction, the same basic construction, and in the details there are differences. So the basic scheme is something that is based on a construction of Nash for isometric embeddings, and so it's an iteration on a triple. So this Q equals 1, 2, 3, so on. This is the approximation of the final solution, and they are supposed to solve the inhomogeneous Euler equations. Divergence of RQ circle and divergence of VQ equals 0. Where, okay, so V and P are velocity and pressure, and this R circle is a traceless symmetric tensor, so symmetric 3×3 matrix. So in principle, you can write whatever F you have here on the right-hand side, the mistake, you can write it in this form. And the fact, so to get a symmetric matrix, you have to work a little bit, and to get the matrix to be traceless, you just subtract the trace and put it on the pressure. So it's no loss of generality to assume that any velocity and pressure, when you plug it into Euler, you can write it with some R. Okay. On the other hand, we want to think of this R as the Reynolds stress at the level of the V, of this VQ. In the same way as in this Konstantin-Ititi proof, this difference between the modification, product of the modification and modification of the product gives you a term of this type, except now I didn't subtract the trace. But you might imagine that if you would have a better way of averaging, not just modification, but something that, let's say, roughly speaking, separates scales and then averages away the fluctuation, then if there is no fluctuation, this would be zero. And the Reynolds stress, also in the physics literature, is the term that comes from the fluctuation. So you have an average V and the fluctuation. Okay, now the basic idea is that, okay, so for us the difference, okay, so WQ will be the difference between VQ and VQ minus 1. You can think of this as the perturbation, what you add to get to the next approximation, or the fluctuation. Okay, and now there are a sequence of inductive estimates on these three functions that have to be satisfied for every Q. And they're going to be in terms of an amplitude delta, or delta to the 1/2, and the frequency lambda Q. Okay, and so, well, you can be a bit more precise even about the estimates, but roughly speaking, think of the WQ, the last perturbation or last fluctuation, to have amplitude delta Q to the 1/2, and frequency lambda Q, which we can write as saying that the gradient is bounded by delta Q to the 1/2 times lambda Q. Okay, and so I'm deliberately also using Q as the index to give you the idea that this is, you might think of this as a Littlewood-Paley decomposition of V. The final V is going to be the sum of the WQs. Okay, so the same way there is an estimate for the pressure, and there is also going to be an estimate for the Reynolds stress. And now concerning the amplitude of the Reynolds stress, here is the first non-trivial assumption. So, since we want to think of this Reynolds stress as arising from averaging the next fluctuation, so think of, remember, I could write the same equation for VQ plus 1, and VQ plus 1 is VQ plus WQ plus 1, and this term arises from averaging away the WQ plus 1, the next fluctuation. And then if you think of this formula, you see that the Reynolds stress should have size which is the square of the next fluctuation. So the natural estimate to put here is delta Q plus 1. Okay, it's the square of the size of the next W. And same way, the gradient is going to be bounded by delta Q plus 1 times lambda Q. Okay, so, and you can write estimates also for the time derivatives. I'm going to skip that part, although it's a non-trivial part. And now the idea is that we want to make an ansatz for WQ, or WQ plus 1, and then show that these estimates hold inductively, and then get a relationship between the delta and the lambda. Of course, if we know how the delta is supposed to go to 0, lambda is supposed to go to infinity, and the rate of the relation gives you a Hölder regularity. Okay, so So what is our ansatz for this function which I call fluctuation? So the fluctuation WQ plus 1 is supposed to have the following form. It's some universal function, capital W, that depends on VQ, RQ, and lambda Q plus 1 times X, lambda Q plus 1 times T. Okay, I'm skipping some details. For instance, this RQ circle is traceless. We can add a multiple of the identity to get a matrix with a trace which should have the same size. But you might think of this as the same as RQ circle. It's not an important detail. The important thing is that this is a function that now depends on two sets of variables. These are slow variables. And since the lambda Q plus 1 is supposed to be much bigger than the lambda Q, this is a set of fast variables. And there is going to be a corrector, which is again just a detail to take care of, because of course I want this function to be divergence-free. Okay, and I can hope to make it divergence-free with respect to the fast space, but not with respect to X here. So there's a corrector. Now this capital W is supposed to satisfy several assumptions. So the W is a function of parameters VR and fast space and fast time, psi and tau. And the first assumption is that in the psi variable, it should be periodic with average 0. So the average, which I'm going to write like this, should be 0. So I'm taking this function in the psi variable, the fast space variable. It should be average on periodic with respect to the unit cube, say, and then I take the average integral on the unit cube. It's going to be a priori a function of VR and tau, but I want it to be 0. The second assumption, since I'm thinking of it as the fluctuation and the relationship to the Reynolds stress should be the following, that the average of W tensor W should be R. So this is something that comes out when you make this Reynolds decomposition into average flow plus fluctuation, write down formally what is this difference, and you get exactly W tensor W. It's the standard thing in the physics literature on turbulence. Okay. Thirdly, I want, of course, if I make this ansatz, I'm going to plug it into the equation and hope that the right-hand side is going to get smaller. It should be an approximation. It should be a better approximation. Now, when I plug this into Euler, okay, I'm going to have to differentiate these two things plus also the fast variables. And when I differentiate the fast variables, I'm going to get a factor of lambda Q plus 1. And I want all of what arises from differentiating the fast variables to become 0, because otherwise it's too big. And this is something that you also have in homogenizations. When you have this kind of multi-scale ansatz, with respect to the fast variables, you end up with a kind of cell problem. Cell problem, which in our case is just, again, Euler, but in the fast variables. So d tau W plus V dot grad psi W plus divergence with respect to psi of W tensor W plus gradient of some similar pressure, which has the same form, should equal 0, and also the divergence in the fast space variable should be 0. So that's the cell problem. And then finally, there should be some natural estimates. So the size of the W should be, so you can think again of supremum norm. should be bounded by, well, coming from this hypothesis, the best you can hope for is the square root of r. Okay, and then in the v variable, it should also be the square root of r. Well, it should not get worse. And then if I differentiate with respect to r, of course, if I think of this as a 1/2 homogeneous function, the natural thing to hope for is r to the minus 1/2. Again, this one just comes from differentiating this formally. Okay, so these are natural estimates that I want for my kind of building block function, capital W. And now, the main question is how to, I mean, why does this ansatz lead to a better approximation? So I want to just very briefly give you an idea of this, and then I'm finished. At least my time is finished. So, you plug in this ansatz to Euler, and then, which I just erased, and then you can write the next Reynolds stress. Well, the divergence of the next Reynolds stress is Euler, and you find an inverse of the divergence. It's not very difficult to construct an inverse. It's essentially an elliptic problem that you have to solve. It's just you have to make sure that it maps into these traceless symmetric tensors. But now, okay, and I just plug in my ansatz, and let us ignore the corrector. So essentially there will be three types of terms. There will be a term which is sort of the transport of the capital W. Then there is a term which is the nonlinear part, divergence of W times W, and I can add, so for the VQ, the right-hand side was divergence of RQ, so I can add it, plus pressure, Q plus 1 minus PQ, and then a third term which is like damping. So it's W times gradient of VQ. Okay, so the first thing to notice is that since I assume, I mean, when I take a derivative of this capital function W, I have to differentiate it in the slow variables and the fast variables. But in the fast variables, I'm assuming that, there is no term appearing. So in fact, these derivatives, this one and the divergence here, are only acting on the slow part of this capital W. Okay? So by slow, I just mean I have to apply the chain rule to this W of V and W of R. Okay? And now when you do that, well, okay, so yeah. So first let me just explain this third one, because this is the easiest to explain. So why should this RQ plus 1 be small? Well, if you look at this function, well, the W in the fast space variable is periodic with average 0. So you can write it as a Fourier series, say ak e to the I k dot psi, where since the average is 0, there is no 0 term. Okay, and this ak depends on the other variables, v, r, and time. Okay. So essentially, and then I'm going to multiply it by something that does not depend on the fast space variable. So also, this function here will have the same form. Okay? So I can just write this W times gradient of VQ has this form, where the AK is depending on V, r and the fast time. Okay? Now, when you invert, and of course, then psi is equal to lambda q plus 1 times x. If you invert the divergence on a function of this form, it has two scales. So it's like semi-classical analysis. You expect to gain a power of 1 over lambda. Okay, so the estimate to expect from here is that this is the amplitude. Okay, I'm referring to that formula. The amplitude in C0 divided by lambda q plus 1. And what is the amplitude? The amplitude is going to be, well, the amplitude of the W is the norm of RQ. And then the gradient of V, all divided by lambda q plus 1. Now I go back to my inductive assumptions, inductive estimates, and get that this is bounded by some expression like this: delta q plus 1 to the 1/2, delta q to the 1/2 lambda q divided by lambda q plus 1. Okay? Now, so this is one of the terms. You have to do the same thing with the other terms, but since it's slow variables, you can again use the same kind of estimate and the inductive estimates. And you're going to end up with terms, again, of this type. So what this is saying is that the new Reynolds stress is going to be bounded by that expression. Now go back again to the inductive estimates. This is supposed to be the delta q plus 1. So this is delta q plus 2. So this is supposed to be of the order of delta q plus 2. And there, now you have a way to get a relationship between lambda and delta. You can do two things. For instance, you could now prescribe that the, maybe I write it here, and I'm really finished. You could prescribe that the delta q is a geometric series. So for instance, set delta, and ignore constants. Set delta q equals 2 to the minus q. Then you plug it in here, and you get a relationship between lambda q and lambda q plus 1. And that relation will be that lambda q is then equal to 2 to the 2/3 q. Is that correct? I hope so. 1/2, no, it's not correct. Well, 3/2 is correct. Okay, but that means that the delta q to the 1/2, which is the amplitude, is like lambda q to the 1/3. And there you have your 1/3. That's the 1/3 that means that, well, amplitude is delta q to the 1/2, frequency is lambda q. So if you have this relation, it means, roughly speaking, 1/3. The exponent of the Hölder norm is 1/3. 1/3 is the border. So now, this is not what we can prove. I gave you the theorems of what we can prove, but this is the basic idea. So what I swept under the carpet is, first of all, to give you the exact way of deriving these two other terms, which are slightly more complicated, and also how to find this capital W. So one comment more is that concerning this first term, to get the same kind of, let's say, semi-classical estimate, it's the same trick, because it's linear in W. But you cannot a priori apply the same trick to this expression, because it's quadratic in W. So if I try to write it in a Fourier series, W has average 0, but W times W does not have average 0. So there will be a zero-order term, right? The whole estimate would fail if I would have a k equals 0 term. But the k equals 0 term is exactly the one that is cancelled by R, and the hypothesis too. So that's precisely the reason why we insist on this hypothesis, So that in this expression, again, I can write it as a Fourier series without zero term. Okay, and since I'm working in a Fourier series, there are no small divisors. If it's not zero, it's at least one. Okay, and yes, so I have to stop here. And if you're interested, I can tell you more about how to construct this capital W. But because we cannot, so if we would be able to satisfy all these four hypotheses exactly the way I wrote them, we would get exactly the 1/3 Hölder continuity uniformly in time. And because we cannot, there are these more complicated statements. Thank you for your attention.